Well, welcome back. What we want to do in this section is look at another form of writing complex numbers called exponential form. So for example, we already know of three ways to write a complex number. The simplest way that we've seen so far is a plus bi, and again I'm going to use I and j interchangeably. We call that complex form, or sometimes we refer to that as rectangular form. But then we also saw that we can express that using the magnitude and direction on the complex plane. Remember what that's called? That is polar form. And then we saw in our last section that we can modify polar form, keep the magnitude, but express the angle in a different way by breaking it into the real and complex components. And we call that trigonometric form. But there's a fourth way that actually works out really nicely for doing operations with complex numbers that represents complex numbers as some power of e. So let's explore that a little bit. Okay, so let's first discuss what an infinite series is. Do you remember what the number e is? That's going to be important for our work for today. E, if you type this into your calculator, and some calculators, most of them require you to put an exponent on that, but E, or e to the first, is about equal to 2.718. It's a function that represents natural exponential growth on things. It's used for a lot of things in sciences, but it's going to provide us another way to write complex numbers. So as it turns out, you can represent or figure out what any power of e does, and this is actually how calculators are programmed to calculate powers of e, using this representation. E to any power x can be found by taking 1 plus whatever that value of x is, plus x squared over 2 factorial, which we'll review what that means in a minute, plus x to the third over 3 factorial plus x to the fourth over 4 factorial, and at that point you can see the pattern. This continues forever. In fact, it continues infinitely, and that's why we call this an infinite series of terms, or an infinite series. Now, a little refresher here on what factorial means. First of all, if you've never seen factorial, the exclamation point is the factorial function. And I'm going to define that really informally. You might have that button on your calculator. But for example, 3 factorial, the numeric value of that is found by taking 3 times every integer below it down to 1. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. 5 factorial? Well, you take a minute. You tell me, what is 5 factorial? Well, 5 factorial is found by taking 5 times 4 times 3 times 2 times 1, and if you multiply all those out, you will end up with 120. And so we could continue that pattern indefinitely. You might look at this expansion and say, that's a little bit out there, but it turns out to be true. Any power of e can be found by plugging in that power into this infinite expansion. So let's check this out. Don't just believe me. Let's use this expansion to figure out what e squared is. First of all, take your calculator and let's figure out what you should get. On your calculator, tell me, what is e squared equal to? And we'll take a couple decimal places on that. Don't just watch me do it. Reach out for your calculator or your phone, for heaven's sake, and tell me, what is e squared? You should get about 7.39 or so, okay? Now let's see if this expansion actually works. If it actually works, then we're going to let x be played by 2, and therefore e squared can be found by taking 1 plus 2, that's our x value right here, plus 2 squared over 2 factorial plus 2 to the third over 3 factorial plus 2 to the fourth over 4 factorial. Now, these terms are getting smaller and smaller and smaller as we go, but if we want any kind of accuracy, we should go a little bit further. Plus 2 to the 5th over 5 factorial plus 2 to the 6th over 6 factorial. And we'll call it good. We could keep going, but the terms get pretty small beyond that. Now let's figure out what that's worth. That means that e squared is equal to 1 plus 2 plus 2 squared is 4 over 2 factorial is 2 plus 2 to the 3rd is 8 over 3 factorial is 6 plus 2 to the 4th is 16 over 4 factorial is 24 plus 2 to the 5th is 32 over 5 factorial is 120 plus 2 to the 6th is 64 over 6 factorial, which is 720. Now again, we could go on, but this will be far enough to prove our point. So take out your calculator and compute this. According to this, e squared should be equal to 1 plus 2 plus 2 plus, that reduces to 4/3, plus that reduces to 2/3, plus, I don't know what that reduces to, but you could type it into your calculator, 32 over 120 plus 64 over 720. That would reduce, but who cares? Just type it into your calculator. Go ahead and do that. Tell me what you get. You should get about 7.36 or so. Does that look familiar? It should. That is pretty darn close to what the actual value of e squared is. Why are we off? Well, because we quit. If we would have continued a couple more terms on here, if we would have said maybe 2 to the 7th over 7 factorial, we would have gotten closer. And we'll continue to get closer. We can get infinitely close by going more and more terms. So your calculator, when you evaluate a power of e, is actually programmed to plug whatever exponent you enter into this expansion, and it tells you what that value of e is. And there's infinite expansions for lots of different functions. So, for example, along with the power of e that we just saw, there's an infinite series expansion for sine of x. Now, x has to be in radians when we deal with the trig functions, but this is going to be important for the work we're going to do in just a little bit. The sine of any angle in radians, x, that's a dimensionless number, could be plugged in, and notice that the signs alternate, and sine uses odd powers of x and odd factorials, whereas cosine of x deals with alternating signs but even powers and even factorials. It's one of the beautiful results in mathematics that sine and cosine can be represented by these crazy polynomials, and sine only uses odds and cosine only uses evens. Now, do you recognize why this is really, really important? Because before calculators, and even with calculators, when you type in the sine of an angle on your calculator, so if you type in sine of 1.7 radians, this is how your calculator figures it out. It plugs in x equals 1.7 into every one of these spots for x, and it computes that. And that's what it puts onto your screen. If you want to know what the cosine of negative 2.4 radians is, it lets x equal negative 2.4, and it plugs it in for x in every one of these slots and puts the result on your screen. The calculator doesn't really understand what the sine and cosine function are, but it does know how to compute them in that way. So this gave scientists and mathematicians a very accurate way to calculate sine and cosine values computationally. It's just a little bit tedious if you don't have a computer or calculator to do it. There's also an infinite series expansion for tangent as well, but it doesn't really do us any good for today, so we'll leave that for your work in calculus. Now, one important consequence of that, and this is sort of what the whole day is based on, is this fact right here. If we know that e to the x can be represented by an infinite series as we just showed, then look what happens if you plug an imaginary number like j into that function. That means that e to the jx, we can plug in jx in every place that there's an x in that infinite series. That becomes 1 plus jx plus jx squared over 2 factorial plus jx to the third over 3 factorial plus jx to the fourth over 4 factorial, and this could go on forever. But we can simplify that, because look what happens. That means e to the jx could be rewritten as 1 plus j times x. Now, look at, in this term, you have a j, but it's squared. So the fact that you've got a j that gets squared, j squared is -1. We bring that in front and this becomes a minus. The x squared stays, and the 2 factorial stays. Our next term contains a j, but it's to the third power. Remember what j to the third is? J to the negative third is negative j. But the x to the third over 3 factorial stays. Now in our fourth term we have j to the fourth, but j to the fourth is positive 1. So this one becomes positive 1 x to the fourth over 4 factorial. But look at what happens if you do that. If we sort these out, we've got a 1, and then we're going to skip a term and move on to the negative x squared over 2 factorial, and then we'll skip a term, and then we have plus x to the fourth over 4 factorial. Every other term matches up with our cosine function. 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, and so on. So all those blue terms combine to give us cosine of x. And look what happens with the ones that involve j. We've got j times x, and then we have negative j times x cubed over 3, and then our fifth term would be similar to that. That almost matches our sine series, except they have these j factors in there. So if we multiply sine by j, then each one of the terms will have a j in it. That's a little bit. And that means that each of these terms add up to give us j times sine of x. So what we can conclude then is that e to the jx is equal to, all the blue ones combine as we saw to give us the cosine of our angle x. And all the red ones team up along with j to give us sine of our angle x. And that gives us the real result that we're after here, and that is that e to jx is equal to the cosine of x plus j sine of x. That's really the star of the day right here, is that fact. But the other consequence of that is, if we multiply both sides by r, you would have r e to the jx is equal to r times cosine over angle plus j sine of theta. And that is to say, we have trigonometric form, which rolls into one more form, that is r times e to the j theta, and this is exponential form of a number. So polar, trigonometric, and exponential form all require our magnitude of our vector r and the angle, but the placement is different. R at an angle of theta is r times cosine theta plus j sine of theta is equal to r times e to the j theta. So let's actually use that fact now. Okay, so we have all four forms of a complex number. We have complex or rectangular form, which we were most familiar with, and then we saw that we could put that in polar form in the previous lesson. We saw that polar form based on the imaginary and real components can go into trigonometric form, and we just saw that this relationship can be expressed as a power of e, and that gave us exponential form. So remember, our angle theta has to be in radians for all these, because in each case, especially you can see it up here in the exponent, that number needs to be dimensionless. It cannot have units in order to go in the exponent. And as it turns out, radians are kind of a dimensionless unit. We've explored that before. So we cannot have degrees on there. It has to be in radians. Okay, so let's write 4 minus 3j in polar, exponential, and trigonometric form. All right, let's get to work. So we know from the work that we've done that the magnitude can be found by taking the square of the real component and the imaginary component, and that turns out to be the square root of 16 plus 9. Square root of 25 is 5. And we also know our angle can be found by taking the inverse tangent of our imaginary component over the real component. Note our quadrant here, this is definitely in quadrant 4. And so if you take the arctangent of negative 3/4, you will get 323.1 degrees, which we have to be in radians here. And so that becomes 5.640 radians. I'm putting radians on there, but remember that is a dimensionless unit. Now that we know r and theta, this is going to be pretty easy. In polar form, we know that this is going to be 5 at 5.640. That one could be in degree form, but we're going to put it in radian form. Done. Okay, trigonometric form, r equals cosine theta plus j sine theta. That's going to be 5 times cosine of 5.640 plus j times the sine of 5.640. Done. There's trigonometric form. And finally, exponential form. Exponential form, our magnitude is 5, e to the 5.640 is our angle, j, done. That is exponential form. Okay, why don't you take a minute and see if you can go in the other direction. I'm giving you this number, this complex number in exponential form, 14.5 e to the 1.92 j. Why don't you take that exponential form number, put it back into trigonometric, polar, and rectangular form. Pause the video, do that, and resume when you're ready to see those answers. So trigonometric form is pretty easy. Our magnitude is 14.5 times cosine of 1.92 plus j times the sine of 1.92. There we go. We've got it in trigonometric form. Polar form, well, that's pretty easy too. We know that our magnitude is 14.5 and our angle is 1.92 radians. Done. We've got this in polar form. So the only real work to do is to put this into rectangular form. We know that our real component is equal to r times the cosine of our angle, and therefore our real component is 14.5 times the cosine of 1.92. Make sure you're in radian mode when you compute that. And a turns out to be negative 4.96. Our b value, of course, is equal to r times the sine of our angle. Our imaginary component then b is 14.5 times the sine of 1.92 radians, and therefore b is about 13.62. Got that decimal point there. And since we know the real and imaginary components, we can say that that number is negative 4.96 plus 13.62 j. Now there's a couple of interesting consequences here. Let's write each of these numbers in exponential form. Consider the number 4. That's a completely real number. So if you were to sketch that on the Cartesian plane, that would be 4 units straight to the right. So we would say that that is 4 at an angle of 0. Okay. Now if we put that into exponential form, we can say that that would be 4 times e to the j times theta. That's going to be j times our angle, which is 0. Or in other words, 4 e to the 0 times j is still 0. But what's e to the 0? Anything to the 0th power is 1. And so 4 times 1 is equal to 4. Let's look at a purely imaginary number. 5j. On the Cartesian plane, 5j is pointing straight up 5 units because there's no real component. So what would this be in polar form? It would be 5 in the direction of 90 degrees, but we need to be in radians here. We're going to call this pi over 2. So when we put that into exponential form, this becomes 5 times e to the j times pi over 2, or in other words, 5e to the pi over 2j. And there it is. We put it in exponential form. What about negative 1? This one's particularly interesting. What will the real number negative 1 look like? Well, negative 1 would point straight to the left with no imaginary component. If we put that in polar form, that would be the same as 1 at an angle of 180 degrees, or we would say pi, right? Make sure you agree with that. The magnitude is 1, our angle is pi. If you agree with that, then we can put that in exponential form by saying that that is 1e to the j times our angle, which is pi. Or if we just rearrange that, we could say that that is, that in fact, negative 1 is equal to 1e to the pi j. Now you really don't need that coefficient of 1, so you could say that negative 1 is equal to e to the pi j. Now stop for a minute and appreciate what has just happened here. We're done. We've answered the question. Okay, let's take a look at this, this result a little bit more closely. So take the result that we just showed, that negative 1 is equal to e to the pi j. Now take that equation and add 1 to both sides. If we add 1 to the left and add 1 to the right, we get 0 is equal to e to the pi j plus 1. Now, look what just happened. A mathematician by the name of Leonhard Euler was the first one to work with this and find this result. This is kind of interesting. The fact that e to the pi j plus 1 is equal to 0 is known as Euler's identity, or sometimes just Euler's equation. Do you see why this is significant? Because there are 3 mathematical constants that are used in all over mathematics, far more than any of the others. Anybody who's done any geometry work knows that pi is about 3.14. That's a very, very famous mathematical constant. If you do any work in the sciences, you learn that e is about equal to 2.718 or so, and that's in your calculator. They both get their own dedicated button. And then if you're at where we are and you've done any work with complex numbers, you know that j is an important number. That is the square root of negative 1. So these top 3 facts, these top 3 constants in mathematics, that they should all happen to fall in the same equation, e to the pi j plus 1 equals 0, and to create a remarkably simple result like that is pretty phenomenal. And Euler, when he discovered this, even though he's a prolific mathematician, this is one of the facts of which he was most proud. Some people say that this equation reveals the beauty and interconnectedness of all of mathematics more than anything else. Anyway, we're going to use this exponential form of a number, which we've now established, extensively in our next topic, because the last thing we have to do with complex numbers is add, subtract, multiply, divide them, and find powers and roots. We'll do that in the next topic. Euler's equation, that we just explored because it's a pretty remarkable result, but it's not going to have big consequences for us moving forward. Okay, that wraps up this topic. So go ahead and do the assigned problems, which I'll send out along with this, and we'll see you again soon.